everyone. Thanks for coming and thanks for your patience as well. I'm Moritz, and Antonio and I are the co-founders of FluidKey. And today we'd like to talk to you about ways to give your users better privacy with stealth addresses. This is mostly coming from the work we've done with FluidKey over the past year, also implementing this for our users. We are first going to show you a little bit of the theory around stealth addresses and how it works, a bit of an explainer, and then we're going to do a session where we're actually going to live code an app that will also generate stealth addresses, so you really understand also at a deeper level how this works and how you can implement this into your apps as well. So that's the plan for today. So for the first 20 minutes, I'll be talking a little bit about stealth addresses in general, how they work, why they're useful, and then I'll hand over to Antonio for the live coding part after that. Along the way, please feel free to also ask any questions. I think it's going to be a longer session, so it's great to make it interactive and kind of also make it more of a discussion and understand how you'd like to use stealth addresses and so on and so forth, if there's any specific questions around this. Great. So with that, let me start by also telling you a little bit more about why stealth addresses are actually a pretty cool way to give your users privacy. The first part, I want to talk to you also a little bit about how we got started. So we are pretty heavy Ethereum and EVM chain users, and maybe I can ask you also a question first. Who here has more than 5 different Ethereum addresses that they own accounts? Okay. 2, 3, pretty much everyone actually, I think. Yeah, so we have also tens of different accounts, right? And one reason we have so many accounts is because if you have one address you tie all of your activity with, anybody can see forever what you've done with this address, who paid you, who you paid, and how much money you have on this address, and so on and so forth. And so what most users do then is like they use their wallet and they just create different accounts for different use cases, and so that's one reason to have many addresses. And that gets really difficult to manage and is also just not ideal, because in the end you don't create a new address for every transaction you make, you just create it once in a while, right? And so you don't have much more privacy and you have a lot of headaches managing that. And so that was kind of also our starting point in exploring stealth addresses, because with stealth addresses you can actually get much better privacy with a UX that's much easier to use than having tons of different accounts across a normal wallet. So a few more questions to also getting to know you a little bit better, just to show of hands. Who here has heard of stealth addresses before? Okay. So half of the room, I would say. Who here has used a product that uses stealth addresses before? Okay, that's great. Then today you will at least get to see a product that uses stealth addresses. We'll build it together. And then the third question is, who here is working on a product that would benefit from better privacy? Okay, good amount of people in the room as well. Great. Then let me start by telling you a little bit about how stealth addresses actually work. I'll start by showing you how this works in practice with FluidKey, just to illustrate this very easily. And then I'll also talk a little bit about the tech behind the scenes. So with FluidKey specifically, the way this works is every user has an ENS. So this is my ENS over here, moritz.fkey.eth. And usually when you have an ENS like that, what happens is every time someone puts it in their wallet and resolves it, the same address gets returned, right? And in this case, it's very different, because every time you resolve this ENS, you basically get a new address. And so you see here 0x78b8. If I refresh the page, sorry, all right. If I refresh the page, what you'll see is that the 0x78 will be gone, and there's a new address here, 0x7fe9. And so every time somebody puts this ENS in their wallet or on Etherscan or anywhere, a new address is generated, and that address is fully self-custodial. Only I can spend the funds that are received through that address. And but this address can be generated by third parties. And so I don't need to be on the other side of somebody having to send me money to create that address in real time. I can just have this ENS in the service with FluidKey, for example, and then this address is automatically generated by FluidKey without FluidKey being able to touch your funds in any way. And so that's the power of self-addresses, because otherwise you could say I can just use my MetaMask or any other wallet and just generate these HD wallet addresses where you can create more and more addresses. But here the cool thing with self-addresses is anybody can generate these addresses on your behalf without being able to touch the funds that go into these addresses. And on the other side, then, inside of FluidKey, for example, you see all of your balances in one place. So here, for example, this is my total balance in this account. But then if I go on chain and look at, for example, this one USDC payment, what you'll see on Basecamp in this case is that, sorry, I might have to zoom in a bit. Yes, you see that this address only holds $1, right? And so I could have $100,000 in this account. You wouldn't know by just sending me money into this address and into this ENS. And so that's kind of at a very high level how stealth addresses work and the benefit of using stealth addresses. Any questions so far, maybe already at this kind of high level? Yes?
If I want to withdraw my funds from a set of addresses,
yeah.
I should provide end transactions.
Yeah. So the way it works is that these stealth addresses. Let me switch back to that tab actually. These stealth addresses are actually counterfactual smart accounts. So the moment you want to withdraw money, it's actually a smart account that is a safe smart account that is deployed at this address. And what that helps you to do is that you can do gas sponsorship, for example. So say you receive USDC in an address. Otherwise, you'd have to fund that address then with ETH. And then, that would dox you because you'd have to send that ETH from one of your other addresses and so on and so forth. And with smart accounts, the other thing is that you can batch transactions. So in FluidKey, basically every time you send money out, the way it works is that we are computing the generic most privacy preserving path for it, right? So say you received $10, $100, and $100,000 in the past, and you want to send $90 out, that would come from the $100 address, because that would just tie one address to that outgoing payment. And so that's one thing. And then on the other side, you can also label addresses and then basically decide, oh, I just want to, pay out this payment from this specific label. So you can also have full control still over which funds you disclose to whomever you're paying. Does that make sense? Awesome. Any other questions? Then let me continue. Yes, let me get back in here. Great. So basically, as I mentioned just before, the big unlock is that you can generate self-custodial accounts for your users that aren't publicly linked to your users, and you can generate as many as you want without them needing to do anything once they're set up. So that's basically the power you get from stealth addresses, and how you can then also provide your users with better privacy, because then in your product, one user doesn't need to be one address, but can be many different addresses basically, and can basically in the end then have much more privacy from that. So also just to illustrate that again, I think right now the status quo is if you have a normal wallet, pretty much all of your transactions coming in and out to the same address, and everybody being able to see your balance, what you're doing, and so on and so forth. And now in this new model, you have lots of different addresses. They're not publicly linked to your ENS, so somebody looking at Etherscan wouldn't know that this is an address that was generated by your ENS before. And all of these addresses are also not tied together. So each of these addresses is its own kind of small account that just holds one asset and isn't tied to any of the other addresses in any way. Now I want to talk also a little bit about the cryptography behind it. So this is pseudomath, right? Not going into exactly how the elliptic curve cryptography works, but just explaining at a very high level as well what's happening, so you get a better intuition for it. So when I receive money from someone that wants to pay me, what's happening is that there's three elements here. every user that wants to use stealth addresses needs to generate what's called a user meta public key. That public key can be basically, put on chain. Anybody can know about it. If you know about that public key, you can't know the stealth addresses just from that. So that's basically the, openly shared parts that anybody can have access to. And then the second part is that you multiply this by a secret. And so this is elliptic curve multiplications, right? These are not normal multiplications. And, that secret is basically what allows you to generate a stealth address. And only if you know the secret can you know the stealth address, and can you know that that stealth address is, connected to the user who has this specific public key. So that secret is pretty important here, because that's what allows you to have the privacy as well. And you can have an infinite amount of secrets, and so you can have an infinite amount of stealth addresses on the other side, right? Now the question then becomes, okay, so now I generated a stealth address for Antonio, for example, and I sent him money. How does Antonio know that a stealth address was generated and that he received money on that stealth address, right? And so there's a few different ways to do it. There's an ERC 5564, that allows you to basically announce these transactions on chain in an encrypted way, where only Antonio with his viewing key is able to decode these transactions and see that these funds are actually, meant for him. Another way in which stealth addresses were actually, created and thought of is that you can also use a trusted third party to basically index these funds on your behalf. And so what that means is that, you don't have to, scan the blockchain for like hundreds of transactions to see if any of those is related to you, but you can have like a trusted third party that basically does that on your behalf and tells you, hey, here there were funds basically that were received in one of the addresses related to you. And then the final part, and this is also how Fluid Key works, is that this secret can be pseudo-randomly generated. And in this case, if it's pseudo-randomly generated, you can basically just replay all of the stealth addresses, because you know how the secret is pseudo-randomly generated, and then you can replay all of the stealth addresses that were generated one by one and check if there are funds on it. So that's another way to think about it, and that's why on Fluid Key, if Fluid Key disappears tomorrow, you can always recover your funds, because these addresses are pseudo-randomly generated based on your private keys, and as long as you have access to your private keys, you can recover all of these addresses without any third party. Awesome. Then the second part is when you want to send money out of the stealth address. How do you? Because this is an address. This is a public key, so it's just a public address. You can't really access the funds from this. But then when you send the money out, there's another set of keys here. You have the user meta private keys, which are basically the private keys related to the public keys here. And if you multiply those by the same secret, you basically get access to the stealth address private keys. And so what's really important here is that the user meta private keys should always stay only with the user and never be shared with anyone, because that's what makes this whole system self-custodial and basically allows the user to have full control of their funds only. And then, the secret is the same secret as this secret. So if you multiply these two things together, you get access to the private key, and from that you can spend the funds of this address. That's it at a very high level. Any questions around this? All right, then let me talk about one more topic, which is the difference of privacy you get with stealth addresses versus other systems, right? So with stealth addresses, you get something that's called unlinkability, and what that means is that you can generate addresses that are not related to your public address and are not related to each other. So they're not tied together on chain in any way. But you don't break traceability. So you can still follow the funds, basically, right? So money that was sent to a stealth address, you can still see where that money came from initially and where it came from, and so on and so forth. And so the advantages of stealth addresses is that they're really fast to produce. You can do that elliptic curve cryptography I was showing to you before. Fully off-chain takes milliseconds, so you can generate them in real time. When this ENS I showed before is, returning a new address. That address is generated in real time, basically, while the ENS is queried. The other thing is that these are just normal Ethereum addresses, and what that means is that they're compatible with, every counterparty and every contract on public EVM chains. That means you can send me money from your MetaMask account, from any other account, and my counterparty doesn't need to know that I'm using FluidKey for this to work, right? I can use FluidKey and just receive payments with better privacy without the other person having to do anything specific on their end. And I think that's really important because most other privacy systems basically require you to have both parties in kind of more of a shielded pool environment where you can then trade with each other, and yeah, you don't need to have that. The downside, obviously, again, is that it doesn't break traceability. I would say it's a downside in one way. In another way, a lot of the users that use FluidKey, for example, like this property because it's much easier to also disclose where your funds came from. And so if you want to off-ramp them or, kind of disclose what how you obtain the funds, it's pretty easy to show because you can show that you have access to this address and you can show where the funds came from. So there's not the risk of you mixing funds with a third party that did something illegal or anything like that, because all of these addresses are fully self-custodial and only your addresses, and you're never mixing those funds with anybody else. And so that's, I guess, the plus side of this property. On the other side, untraceability, so meaning that you can break the path your tokens took. So say somebody sends you USDC and you want to, make sure that nobody can know who sent this USDC. That's what's called untraceability. And that is enabled by systems like privacy pools, like Tornado Cash, for example, as well. And I think the downsides versus stealth addresses is that it's much slower, right? So you have to move your funds into this shielded protocol, and it'll take multiple hours for you to basically be able to take them out safely with privacy, because otherwise if you just move them in and out at the next second, you basically don't gain anything because you can tie those those movements together. So usually you have to leave them in a system like Railgun as well for at least 3 hours, and so that's like also a little bit of a slower thing. The second thing is that you have a limited set of operations you can do within a privacy pool, right? So you can maybe send money to others, but they also need to be part of that system. And then you can do in systems like Railgun, for example, you can do swaps and a few other things, but you can't interact with every contract on an EVM chain just like you would do with a normal address. And so that's another downside there. The plus side is that it breaks traceability. So that's the really big plus side on that side. And so what we think, is kind of the ultimate privacy stack in the future is that you kind of combine these two things together and have something where you have stealth addresses where you can, receive payments day to day very easily without your counterparty having to do anything on their end. And you can just interact with any contract through that. But then if you want to break traceability on your end, say you receive $1 million and then you want to spend on the other side smaller amounts with that, you receive your $1 million into a stealth address, pass it through a privacy pool. On the other side, you can send that to many different stealth addresses of say $10,000 each. And then you can spend from those stealth addresses and just interact on chain with those addresses as well. And so you get that break in tracing, but also benefit from having addresses that are just compatible with any contract and anything on chain. And so yeah, that's kind of where we're seeing things going. But there's a lot of work, I think, on both sides, both on stealth addresses and privacy pools still to be done to make this super user friendly. And so we're really also focused on that. Any questions on this part? Then the final point I want to make before I hand over to Antonio is talking also a little bit about the UX problems to solve still with stealth addresses. Two specifically. One is key management. So the way stealth addresses work is that you have, they're basically EOAs, right? And then you can have an EOA that controls a smart account. So if you have basically a 1 out of 1 safe, for example, with an EOA that is a stealth address. The problem with that is that if you have thousands of different addresses with those keys, if you want to rotate those keys, for example, you'd have to do 1,000 on-chain transactions to rotate those keys. So that's not really practical. And you also have the issue then that, if you rotate the same keys at the same time over 1,000 addresses, you can link all of those addresses together and so on and so forth. And there, we're really excited about what's happening with key store rollups. The idea with key store rollups in a really quick explanation is that you decouple the smart accounts from the keys themselves. So the keys are stored in a key store rollup or a smart contract, basically, where you have a slot for every user. So the user A says, these are my keys. And then every time you deploy a smart contract, a smart account, you basically point to that slot in the key store. And by doing that, you can just rotate the keys in this one key store slot, and they automatically rotate your keys on all smart accounts that are pointing to that. To do that privately, obviously, you can't just point directly to that slot. Obviously, otherwise it would tie everything together. So you need to have ZK-proof signatures and so on. And so, there are like proof of concepts around this, but this is all still pretty much in beta. And so this is something that I think we'll see a lot of improvements around as well in the coming months. The second issue is around dApp interactions. So say you have all these stealth addresses in FluidKey, for example, and you connect to Uniswap, right? And then you want to, swap some of your funds. How do you do it without having to move all of your funds to one address? Because when you connect to Uniswap, for example, you have to connect with one specific address, and Uniswap would look on-chain the balance of this address, right? And so you need to have enough balance on that address to be able to make the swap right now. And that's a huge problem, because then you have to move funds before even making the swap and so on and so forth. With ERC 5792, wallets can basically communicate to dApps what properties the user already has. So the wallet can just say, FluidKey can just say in this case, for example, hey, this user has $100,000. We're not telling you where these $100,000 are, but they're here, they're 100,000 USDC somewhere. And just assume that that's true, and then prepare the transaction for us. And then at the moment of the signature and the transaction being executed, that's when we then, in that transaction, also move the funds to the address. But the user doesn't have to move funds before executing any transactions or interacting with any dApps. And so that's, I think, also a big UX improvement we need to still work on, and that's being worked on with ERC 5792. That's it from my side. Any questions before I hand over to Antonio for the more practical part? Yes. This one?
Yes, this one. Did I correctly understand that this pub key and private key is the same that extended public key and extended private key in BIP 32 HD wallets?
Yeah. So the key is a bit different. So there's different ways to kind of do it, and I think Antonio will show you concretely how it looks, for example, with FluidKey. Usually with self-addresses, you have a viewing key and a spending key. And so you kind of have like two keys, actually. And the spending key is there to allow the user have access to the funds, and then the public key is there to multiply by the secret. But yes, you're correct that in the end these are just like Ethereum public and private keys. So it's it's kind of similar in the sense that they're the same kind of private keys and public keys.
So the function that returns me stealth private key is multiplication extended private key by secret. And if I want to get stealth public key, the function is the same. Is this private key, stealth private key, matched to stealth public key?
Yes, so the private key and the public key are connected together, exactly. They're like one set of keys in a way, right? It's like the same way when you have your normal Ethereum account, you have like a public key and public address, and then you have your private keys that can control that.
Yes, but in BIP 32, this functions is not the same. Not multiplication in first, not the same that multiplication in second. It's more complex.
Yeah, I think for sure it is more complex. So again, this is like a simplification just to explain at a very high level, you know, get an intuition for it. Antonio will, I think, show you the code exactly how it works.
Thanks.
And maybe then you can ask questions if it's, unclear. Awesome. Any other questions? Good. Then, let me hand over to Antonio for the second part of this session. Over to you.
Thank you, Moritz, for the intro, and hi, everyone. I'm Antonio. I work as a CTO at FluidKey, and today I want to try to show you in practice how stealth addresses work. To do that, let me show you the structure of this project. You get a screenshot of how it looks like at the beginning of the slides. In the end, will be a React app, a very simple app we run on localhost. There will be also a deployed version of it at the end. We'll show you. What this app does, the app will manage and create stealth addresses locally. And then through Wallet Connect, we will try to connect to the safe app web UI, and we will deploy a safe controlled by one, or you can even play around, so even more of the stealth address you generated. And this basically allows you to have different safes controlled by different addresses. So apparently they seem completely disconnected users, but under the hood, all will be controlled by the same user and the same master key. Now we will get familiar even more with the names of the different parts that compose stealth addresses. What this allows you to do then, of course, is then through Wallet Connect, maybe connect this safe to any DApp. As Moritz mentioned before, these are regular stealth addresses. So connect to any DApp and do literally whatever you want, controlled by your stealth safe. So this is the goal of today. The couple of notes on the implementation details, and this is where I want to step in. Stealth addresses are, in some parts, are also concepts, and this is what matters most for me to give you today, is that there are some parts, like the elliptic curve multiplication, that these are mathematical constraints. So we cannot change how those things work, otherwise stealth addresses won't work anymore. But to get there, there are some steps that are conventions, but not like conventions that someone imposed with an ERC or whatever. They are ERCs, okay? But there are parts that can be interpreted or done based on what are the needs of what we want to do. And these are the implementation details for the demo of today. First of all, we use the way that fluid keywords. Stealth addresses are pseudo-randomly generated. This means that if you have the viewing private key, and then we'll enter more into details, you will be able to regenerate those addresses. Okay? It's a private key. It will stay with you. But that's how you will be able to regenerate in a way that if a third party disappears, you will be able to regenerate those addresses always the same way. We will use the viewing key. So now let's start getting familiar with these names. When a user wants to generate stealth addresses, on convention it's two keys. One is called the viewing key, the other one is called the spending key. Together, they are the meta stealth key. So we get familiar with names. Why they are separate, why there are two, we'll see it later, but it brings a lot of practical advantages when you want to self-control funds, but let someone else generate stealth addresses on your behalf. As I mentioned, these addresses can be easily recreated in the future. We don't need to emit an on-chain event because everything will be run locally. And this is meant for trusted third party or personal project. Think about, you want someone to set up, with this example, you want someone to set up safes on your behalf, safes that only you can control, but you don't want to be there every time to tell them, oh, this is my address, this is my address. And you don't even want to send him a list of pre-generated addresses that you can control. It's enough to share the viewing key with that trusted third party. That trusted third party will generate the safes for you, and then whenever you want, you will be able to move money out. No one will be able to do that unless you. This viewing key should be kept confidential. I mean, you can share with trusted third party. If you share with anyone will be able to compute your addresses. That's it, that part. To simplify this workshop, we have used the Stealth account kit. It's a SDK, JavaScript SDK that we coded. It has been audited back this June. And we will go also in the code of this kit, but this will allow you to create an app generating and controlling stealth addresses within really a few lines of code. And that's what we will do in this workshop. We will have 3 goals for this workshop that are the 3 main phases that also Moritz showed before in the slide where he was showing how stealth addresses work. First goal will be generate the meta stealth keys of the user, so the spending and the viewing. Goal number 1. Goal number 2, generate 1 or more stealth address. Goal number 3 will be generate the private key to control those stealth addresses. I on purpose separate phase 2 and 3 to show you that it's possible to generate a stealth address without knowing its private key, then generate the private key to control that address knowing the spending private key. I know, it's quite a lot of things, so we will tackle one by one and we will go into that. So now let's go to code, and I will leave this for you. So the way it works, I've created this GitHub repository. It's under fluidkey/DC7 stealth address. I will leave you time if you want to clone it. This repository has a main branch and 3 branches called stage 1, stage 2, and stage 3. I've set up it in this way because we will start coding from stage 1. So if you want to code along with me, just clone stage 1. But if for any reason you messed up, you lost a piece, you have an error or whatever, once I move to stage 2, that's when we will create the stealth address. It's enough for you to pull the stage 2 branch and you will be up to that point. And at the end of the session, we will be at the main one. So the main one is the final version that we are going to code today. You don't need to understand how React works. You just need, and there are instructions on this repo. So let me go here. This is the repository. You will just need to clone and run yarn install and then yarn start to have the app going. And we will add code just in one file. So just make me sure that I am on stage 1. Perfect. So I'm stage 1, and this is okay. Now we need to zoom in. And how's that? That works like this. No. I even zoom out. Okay. Much better, I would say. Can you read it, or you want bigger? Okay, if you don't see something, just raise your hands. And you want bigger? Sure. Okay, I think that could be better. In general, if you need to ask questions or if you miss a part, just stop me, and I don't want to lose anyone on the path towards the goal of this session. As I was saying a second ago, I've already run yarn install or npm install, whatever it's best for your laptop, and now I will launch the application with a start command. Yes? Sure. Don't worry. So the repository is github.com slash, no, sorry, that's the wrong one. github.com slash fluidkey slash DC7 stored address. So let me go back to the slide so you can see bigger. Don't worry. Perfect. Let me, meanwhile, go back here. So I have just hit start. Let me also open the console that just will help us going through what we are doing. So again, I just clone the repository, yarn install, yarn start, and you will have a fully functional React application that technically, if you get there in a website, you will say, oh, okay, just generate a master key. If you click that, it says, oh, generate metastyle keys not implemented yet. And that's the first task we need to go through. Now, this is a demo application, okay? So I have removed some parts that in a regular application you will have there. The most practical and hopeful one will be to have a connect wallet button, like if you want to connect your MetaMask into this. To simplify that part and avoid a lot of problems, so my MetaMask doesn't connect and so on, we will generate a private key right here, and from that private key, that's like if it's your wallet private key, we will generate the metastyled keys, and I'll show you how to do that. Again, this is a demo application. If you want, after the session, to propose a PR and have a proper connect button, feel free to do. The code is open source, and you can do whatever you want. Okay? So let's start coding this first part, and let's go into our project. In the project, there is a, I'm sorry, this part I cannot zoom, but there's a source folder, src folder. Inside, there is an helper folder that has a file that's called storedaddress.ts. Again, I don't know why it's losing the zoom. Perfect. This is the only file we are going to edit. And this file has 3 functions, one for each step. The first function is called generate metastyled keys. And at the moment, you see there's an alert. That's the alert we just saw in the code. Okay? If you scroll down, there is a second function that generates styled address. That's the second function, second stage of the workshop. And then the third one, that's the eval styled address private key, and that's the third stage. Once we get down to this point, we will be able to have to deploy a safe and control the safe with the address we are generating. I have set a lot of to-dos that will guide us through what we have to do. And if you don't mind, I would like to start with the first step. So let's see how to generate the metastyled keys. As I mentioned, for this demo, I have simulated I don't want to connect an external wallet, just to simplify. But on average, what you will mostly commonly do to generate a styled addresses is ask the user to connect a wallet and generate and sign a message. The signature is a deterministic signature. This way is a nice way to ask a user a unique string, the signature, that only his private key can generate, and you know that it's tied to the user master private key without asking the private key to the user, the wallet private key. Okay? Because if you go on a website and the first thing you ask a user is, can you please pass here your private key of your wallet, that's like, it will be targeted as a scam website, your application. So you cannot do that. Here, what we have done to simplify, we just generate the private key here. You will see that key appearing here. And we will think about a message. In this case, I put hello Devcon 7. This is the message that must be always the same to always obtain the same signature from the user. If we change this message, the signature changing and the meta-stealth keys under the hood will change. So let's keep it static. We will then input to this function a private key, a wallet private key, and we will return the spending and the viewing private key. The first part, out of these 3 internal steps, 2 of 3 will be very simple VM function. So let me go to the first one. I will just create an account by calling the function private key to account and passing the master private key receive as input of this function. Let me go a little bit. Okay, so this function has a master private key, and this generate an account. This is exactly as having a MetaMask account connected. Okay, so nothing more than that into that. This is again a VM function. And the second one, I want to obtain a signature, and I have to use the await. It's an await. Yes, account dot. Okay, assign message, but this is wrong. And we have to pass the message to authenticate, and that's done like this. And again, if this account represents a MetaMask wallet connected through WAGMI, for example, this is exactly how you have to do. Just require a message, and there is an await, because the user will have to click and approve the signature. And now we have obtained a signature. That's everything. That's the last part, not related to stealth addresses. From now on, will be only stealth address related functions. And we will use the first function from the stealth account kit. So we need to, let's read the comment. Use stealth account kit to derive meta stealth keys from the signature. I think it's time to go back into our stealth account kit. Let me maybe still zoom a little bit more. That's it. I don't know how to close this, honestly. Let me see if I can. No, more than, but it's fine. If you go into our stealth account kit, or you clone it in the source folder there will be a series of functions. To simplify, we put one function per file. That's easier also to read. Each one will be used at a certain stage of our workshop. What we will need now is generate keys from signature. Just quickly showing what it does. Basically, this function takes a signature and returns the spending and the viewing private key. How it does? Very simple. Take the signature, split by 2. Each part of the signature is used as an initiator to generate a key, and then returns the 2 keys. You don't have to write all this code. You just need to go here and says generate keys from signature, and you pass the signature. And then, of course, we need to store that into function. And then we need to return keys.spending private key and keys.viewing private key. Okay, this you start seeing the utility of the stealth account kit. You don't have to know all that part. This specifically part is a convention. It's not a must to do for stealth addresses. In your app, you want to generate the viewing and spending private key independently with your algorithm. That's fine. Okay, it's not something that you have to do. This is the easiest way so that a user can connect this wallet, generate a signature, and make sure that even if your front end disappears, he is always able to generate a signature and then following a simple program being able to generate the keys. Let me also put here a console.log of keys, and let's see if it works. Now let me just clear cache, go back to console, clear it, refresh the page. So before we were here, and when we were clicking the button, we were getting an error. Now, let's click the same button, and we get keys, okay? And as you can see, this is if you go in the React code, it will generate a random private key. Of course, if I copy it, I clear the cache, and I pass this key inside here again, the metastyle keys generated that we can see here will always be the same. So this 0xD8BC as a spending and 0x8944AB as a viewing private key, they will always be the same. If this changes, all the stealth addresses are going to change. Okay, so that's the first part. Stage 1, completed. If you didn't follow along, you can pull stage 2 of the GitHub repo, and you will be exactly at this point like I am now. We are ready to go into the most interesting, I would say, part of the process. That's generating the stealth address. That's also the one that requires a little bit more of steps. And in our React application, it would be just, okay, generate your first account. If I click, this application allows me to add also a nickname, whatever I want. And if I add, now I got a message. Generating stealth address is not implemented yet. And this is what we will do in the stage 2 of this workshop. To the console and go here. So let's start by removing this alert. And as you can see, this generate stealth address has 2 input parameters that are set by the React application and needs to return 2 things. So, sorry, it has 3 input parameters. The first one is the viewing private key. The second one is the spending public key. And the third one is a numeric nonce. First thing you notice, there is only the spending public key. Because it's a public key, I can share with anyone. And this is what guarantees me that my funds are self-custodial. To generate a stealth address, you just need the spending public key, not the spending private key. And this is the first important part. The second part is the nonce. The nonce is a number, can be any number up to 2 power 256. Okay, so like a large amount of number. For simplicity, in this demo application, we will rotate from 0 on. So we'll pass the nonce 0, 1, 2. The changes of this nonce will change the generated stealth address. So once we have once you have the meta stealth keys, then it's just enough to increase the nonce, and every time I will generate a stealth address that's completely uncorrelated to each other. And even if you know the 2 addresses are controlled by the same private key, let's say I generate 3 addresses of you, out of these 3 or any address, I am not able to recreate the controlling public or private key. What this function returns? This function returns the stealth address and the ephemeral private key. And now you're asking, what's an ephemeral private key? In the high-level slide we had before in the Moritz session, at a certain point there was the public or private key multiplied by a secret. That secret is obtained from a mathematical operation we will see from a ephemeral private key. This private key can be generated by who generates the address, generate the address to that, and then can throw away the private key and just keep the public key. This, I don't go into too much details. At the moment, just consider that you need also this private key, but it's a randomly generated private key at the moment, or pseudo-randomly generated if you want to recreate them consistently, and this is what we will see now. Also here, 3 steps, all 3 related to stealth addresses, and this we go back into what I consider convention, not a mandatory mathematical operation you have to do for stealth addresses. When we decided to know how to set up fluid key, we thought that sharing a viewing key, even if it's a private one, let's say it in another way, sharing a private key, whatever it is, it's always a bad attitude. You never have to share a private key. But as a trusted third party, I need a viewing private key to generate stealth addresses on your behalf. So how did we end up solving this problem? We ask user to share with us a BIP32 node of the viewing private key. See, in a simple way, you have a viewing private key, the one we console.log in the browser before. And from that viewing private key, you are generating a sub private key that you share with us, following a standard that's the BIP32. Why? You say, why that? Why this extra complication? Because the day you don't trust me anymore, if you have shared with me your viewing key derived from the master key, you have to change the master key. And those changing also the spending key and all the others you have, you need to go through each of those and change the controlling key. If you have shared with me a private key derived for your viewing private key, the day you don't trust me anymore, you just need to start generating stealth addresses with another sub-viewing private key, and the spending key stays the same. So I, as a trusted third party, know all your addresses up to that moment, but I don't know anymore your addresses from that moment on, while you keep controlling also the next addresses with the same spending key. This just to say that in a couple of lines of code, we will generate this sub viewing private key. We will call a viewing private key node. And we will use the node number 0. Of course, we are just generating now, we use number 0. The day you don't trust a trusted third party anymore, it's enough to put this as 1, and you will start generating other stealth addresses, controlled all by the same private key, but the other party won't be able to know that are your addresses, those. First step is use a stealth account kit to extract the specific node from the viewing private key required for generating the ephemeral key. So what I just said, we are going to do with a one simple function that we take from the stealth account kit. And if you look at the list of function, it's called extract viewing private key node. And as you can say, we are just using, this is, I'm not going to details, but it's a standard BIP32. The purpose is 5564. We use this number because it reflects the ERC around stealth addresses, but nothing special around that. And the node is the number we just said, 0, 1, 2. Every time you change the node, the derived viewing private key completely changes. So this function accepts two parameters, the private viewing key and the node, and returns a node. The HT key is a node. So if we go here and just const viewing private key node, as you can see, it already knows what I need to do, and yep, and this is the implementation. So basically, I am extracting the viewing private key node, passing the viewing private key, that's an input on the function, and the current node number, the number 0. We can pass this node number as a parameter of this function, yes, of course, but it's usually it's something that you change really once in a while, so for the demo it's fine to have in the code. Finally, we have the viewing private key we will use to generate all the stealth addresses from. We can go to this next step, and here we have to use stealth account kit to generate an ephemeral private key using the extracted viewing key node and the provided nonce. So we will use this just generated key to generate this ephemeral private key. That's basically what forms the secret that you just showed before. Okay? We need this one to generate the secret. when in the slide before we were putting secret, we were hiding this intermediate passage that's needed at code level. To do that, let's go back in our stealth account kit and the function that we'll need to use. It's the longest one, actually, but generate ephemeral private key. That's it. This function accepts 4 parameters. Actually, 2 are mutual optional. The first one is the viewing private key node. That's the one we just generated. Okay? See it as a viewing private key, but in a way that if I want to rotate it, I don't have to change my master key. The nonce is the one that we passed. The 0, 1, 2, 3, 4, that every time we change the stealth address generated. So this changed quite often. This is why we put as an input of the function. And then the chain ID. That's why you can generate stealth addresses specific for a specific chain. Here, we will pass chain ID 0. What does it mean? It's an address that you in your mind can use on any chain, not on just specific chain. Okay? Why this is done? Because sometimes you want to force some addresses from a logical point of view. It's not like from a practical or mathematical point of view to work only on a specific chain, because you will deploy a smart contract controlled by that stealth account that's available only on one chain. Okay? And that's an easier way for you to generate stealth addresses that are for you connected to a specific chain. Again, this is a concept, not a mandatory mathematical constraint. The nonce should be to get different stealth addresses. So the question is, like, I have a nonce, can I just change that for different chains? If you think you want one address for one chain, works. The moment that you might have 2 addresses for the same chain, you might not remembering that. The approach we do, for example, at FluidKey, we have always chain 0, and we deploy safes, because we have safes, through the canonical factory that generate the same address, the same smart account address across all the chains. So we don't have this problem. And also it's an advantage, because if by mistake I send money to the wrong chain, I know how to recover that amount of money. Okay?
The chain ID is never, I will see. Reviewing with the current chain ID, you can choose anyone that you want, that you like.
Absolutely, absolutely.
Instead of 0, you can choose 2 power 256 minus 1, and
yes,
it's done again.
Absolutely.
Perfect.
Again, this is a concept, not a mathematical constraint. So
Perfect.
whatever you want. So let me go here. I put this, and then let me. My bad. And okay. These are type parameters. So the viewing private key node is the one we have above. The nonce is the one passed to the function. And the chain ID, we said we're going to put 0. And this returns a ephemeral private key. Feel free to go through the code. The idea is that we also do here BIP 32, that just to stay in the standard. I added a lot of explanation around what it does. I don't want to deep dive, as I think it will remove the focus from what we are doing now. And finally, so that I can finally see the stealth address being generated, we will use the stealth account kit to generate stealth addresses using the spending public key and the generated ephemeral private key. If we go to the stealth account kit, there's a function generate stealth addresses that accept an array of spending public keys. We set up an array because you can generate multiple addresses in one shot. And the ephemeral private key. So This is the function. Technically, might have picked this up. The problem is that this needs to be an array. And probably misses an S here. Perfect. And now we can return the stealth address generated and the, okay, like this, because it returns a type 1, and then the ephemeral private key. I could have also technically returned ephemeral public key. No, that's just more to keep those connected to each other as I've generated those stealth addresses. Now, with the setup of, okay, I have the viewing private key, I extract the node, I generate the ephemeral private key, so basically I generate the secret, let's see in this way, and from the secret, I generate the stealth address. If we want to go into how this function works, this is what probably you were mentioning before. You will see that to obtain the stealth address in the function, I do an elliptic curve multiplication between the spending public key point and the hash of the shared secret. The shared secret is an hash, the hash of the shared secret comes for the shared secret, and the shared secret comes from the ephemeral private key and the spending public key. Okay? Again, these are the advantages of using the stealth account kit. You don't have to remember all these steps in memory, just use a function, but that's just to prove you that there's elliptic curve cryptography under the hood. Now, I'm confident that if we go here and we click generate your first account, and we add, the account appears. Now, if you add another account, another one appears. And if you add a third one appears. All are different. This has nonce 0, nonce 1, nonce 2. If we look on them on chain, we will use base chain just for simplicity. It's an empty address. There's nothing on it. It has no connection to each other. It's also empty because we have just generated them. No, but that's to prove you the power of this tool. Now we can go to start doing the fun part and try to deploy a safe controlled by one of these. To do this, we will need to wallet connect to the safe UI. And we are using wallet connect, so please finger crossed that it works. I've set up this here. Let's see. Amazing. Now, what does it want? Strange, because I was pretty sure I added this AP. Maybe my bad didn't update the code. Oh, strange. It's here. Why does it complain? Moritz, an idea? Pop. Well, pretty strange. But let me see. Well, seems to go now. I don't know why. But it's done. It's 954 because yesterday we had this same issue, but 954F. It's right here. So if I continue with that, let me deploy this on base. Of course, as you can see, I have connected a specific stealth address, 954F. That's the first one in the list. I want it to be deployed on safe. 1 out of 1, it's fine. And just pay now. Luckily, safe allows a sponsored deployment. So that's it. I don't have to approve any transaction. And in a few seconds, the safe will be deployed on chain. And we will have address connected to that. Let's give a second that it deploys. And then we will move actual money on it. We'll move a few cents of it. And then the last part will be try to move them out. And we will need to create the private key for that. This is the safe generated. It has an address, F7A1, blah, blah, blah. Let me switch to base also wallet connect. So that's All here, all done, perfect. Now, I have the address, and I will send money to this address. To do that, I will use my FluidKey account just because it is faster. Let me send like 0.00001. What's that? 3 cents? Yes, of worth of ETH, and this is the F7A1. Double check F7A1. Perfect. Send pin. As you were mentioned before, FluidKey relays the transaction for you. Under the hood, this money is coming from a stealth address, a stealth safe. Okay, I'm just using that to simplify the process. Okay, so money is being sent. Yeah, so the safe I deployed here, I basically told the safe UI, this is the signer, and it was one of the stealth addresses I generated. Trust me, I have the private key, because I connected through Wallet Connect. Then safe deploy the safe, because we are on base, they sponsor the transaction, it's gasless, they pay the gas for us. Coinbase is sponsoring the gas. And that's it. We have a safe control with a 1 out of 1 signature from this stealth address. What we will have to do is generate the private key to move this money out. If we go to the assets, we have just received 3 cents worth of ETH now in this safe. Now, if I want to move money back, let's send this money back to my account, but we have stealth addresses, so back to another address of myself, and say, okay, I want to empty it, send it all out. If I go next, it works. I mean, it's the saved UI. It's just simulating. I say, okay, wonderful. Execute it. Now, when I execute, if I go back here, it throws me an error. It says, evaluating stealth address private key not implemented. I cannot, do the transaction for you. And if I go back, there is a user rejected signature. There's an error. So we have to fix this error, and we should be able to move money out and complete the workshop. This is the easy part of that, because the hard part we have already done. The easy part is just one function, and you can pull stage 3 if you want, or that's the last part we have. And we have to go to the evaluate stealth address private key. So let me remove the alert, and I need to use the stealth account kit to generate the stealth private sending key using the provided spending private key and ephemeral public key. So here is where I need the spending private key, and that's the only time you have seen me using that, and the ephemeral public key. Spend like 1 minute explaining why I need the public key here, but it's also a logical way of doing that. You never have to share a private key. So if I'm in a scenario where I want to generate the stealth address for you, for example, I don't share the secret, because if I just share the secret, everyone will be able to see a secret, and everyone will be able to do the computation, understand who is owning that address. I generate an ephemeral private key that allows me to generate a secret. Then I share with you the ephemeral public key that you can use to generate the same secret too. It's a lot of elliptic multiplication, but this allows a trustless environment where there's no risk of encrypting stuff on chain, because if you encrypt something on chain, today is encrypted, who knows in 10 years if that same stuff is still encrypted, or someone can broke that encryption on chain. So this is really one line of code with one function. Let me go here for the last time and the stealth account kit and get a function that's called generate stealth private key. And if you enter and you see how it is, it's very short. You input the spending private key and the ephemeral public key, the same input we had in our function. we recompute the share secret. Of course, the output of this computation is the same of the one we do when we generated the address, but this time we multiply the spending private key with the ephemeral public key. If you remember, before, to generate this secret, we multiplied the spending public key with ephemeral private key. Okay? So all the pieces are coming together, and I am able to regenerate the secret, hash it exactly like we were doing before, and doing a slightly different elliptic multiplication. That's not like proper multiplication because we have like then to limit for the end of the curve and get the private key. From here, we have the private key. And if we input to see if that works, to see, we get here, maybe got it? Yep, perfect. And that's it. But we'll leave the code for here. For sure, it's not like this. It's like this, because it returns a type parameter. So I have just called the generate still private key. The function I just showed you runs under the hood and returns me the private key that I return to control the transaction. And for example, how this code works, the private key is generated only at the time of the transaction. I don't keep store private key that I don't want to store, and after is thrown away. Now, if we go back to our safe wallet and I ask again to execute the transaction, and I go back here, technically, finger crossed like before, yes, it works. Forget about the error just react. We have received a signature request from MetaMask. See, MetaMask, good night. From Safe. This is the body of the transaction. If I approve, I'm using the stealth address private key just generated to confirm the transaction. And if we go back here, try again, maybe it was timeout, something like that. Let's see. Okay. Tack. Okay. Of course, it's the beauty of the okay, somehow the connection with Wallet Connect broke. I have no idea why. So that's why it wasn't working, because Wallet Connect was no more connected. Now it says it's connected. Let's try last time. So this is where I want to send the money. I want to send it all. Next, prepare a transaction. Otherwise, I will reset the connection with Wallet Connect. Let's see if it works. Okay, let's approve. No, there is something it doesn't like. So I know what to do. Disconnect. Refresh. Request to connect again with Wallet Connect. Regenerate the connection. Amazing. It's connected. 095. Perfect. Try to execute again. One last time. Let's approve. Perfect. And now it worked. This is why I was asking you to keep finger crossed with Wallet Connect. So if you notice, we are sending money back to the account that sent me. Actually, we are sending money back to another address that sent the money, but controlled by the same owner. And this is the power of stealth addresses. If you look on chain, you will see money coming from A to B and B to C, and you have no idea if A and B are the same owner and C a different one, or like in our case, A and C are the same owner, and B was just a middleware we sent money through. As you can see, we just received 0.0001 ETH, that's like 3 cents. And if I look at that on Basecamp, I will be able to see that it was sent to this address that has just 3 cents of worth of ETH, while in my wallet I have $5. You can do a lot more. I'm not doing that now. I want to leave some space for the questions. You can, for example, wallet connect SafeUI to Uniswap and control it. Add another signer. Generate a 2 out of 2 signer by, for example, here in the settings, add another signer, and this signer can be another stealth address of the one you generated. And you say, why doing that? I have no idea, but maybe you want to show that you have 1 out of 2 or for some reason, and I'm adding a second signer to that, and so on. I'll go back to the slide, but there's time for questions, and that was my main concern, is leaving like a 15 minutes to discuss and go on. You can find the final version of this demo app on dc7.fluidkey.com, just in case you want to play it a little bit around, and make sure also to check the repository. I will also add the link to the repository on this page now. It's currently missing. And one last slide. If you want to learn more around the stealth address or you want to start building, please scan this QR code. We have put together a series of links and useful links to learn more about that. And there's also a link to our stealth account kit, the SDK we just used. There's also a Telegram group specific for stealth addresses. There are like nice discussion going on. If you want to be added, just send a message on Telegram to Moritz_fluidkey, and we will be super happy to add you to that Telegram account group. With this, if they are open to questions, but thank you so much for your attention on behalf of Moritz and myself. Thank you. There's a question there. Behind you? Yep.
For me, it's still not clear how each key relates to each other. Like, can we somehow explain it maybe with math or with simple slide if you have? I understand that you need to arrive to the stealth private key and public key, and the path to go there should be like through different keys. Yeah. Could you please explain math behind it? Like.
At the beginning, just to understand, because we showed one slide with the receive and send. Did you see that?
I watched it on YouTube, so
okay.
maybe.
So what wasn't clear from that slide, maybe, or like how?
Let me go. Yes, better with the mic. Exactly. Perfect. Okay.
Yeah, here we go. So yeah, basically the whole point of stealth addresses, right? Like again, otherwise you could also, if you want to generate a new address for yourself, you don't need stealth addresses because you can just use like an HD, path to like create a new address every time, right? And that's controlled by the same private key. The whole power of stealth addresses is that you can share a public key with anyone you want, and then they can share an address. They can create an address on your behalf that they know only you can basically control, right? So in the case of what we built just now, one example is, for example, say you're getting added to lots of different multi-sigs, right? And you don't want your main address to be added to it, but you also don't want to generate like lots of different addresses yourself in your MetaMask. You just want to share, basically your meta public key, and then anybody adding you to a safe can basically just generate a new address on your behalf, add you to that multi-sig, and you'll have full control and basically access to also control that. That's again at a maybe high level. So is there like what do you like? Yeah, maybe you can explain better what you're not.
Yeah, like you shared with them public ephemeral key and how they can generate additional address for you. Is it or what do you share? I think.
Yeah.
It would be better if you explain the specific math of multiplication of elliptic curve equations if you have, because it will be more clear.
Sure. So I think we can go to our repo maybe and show you that.
The public one, start from the generate stealth address. This one. It's a little bit more.
Awesome. Do you wanna run through it, actually?
Yep. So this, why? I will just point with this. This line here, still public key, is spending public key multiplied by the share secret. Okay, this line here is on the slide. This line here. Okay, to get to this one, we need to generate this secret. The secret here, forgetting about like generating a random one, like how we implement it here, we generate a point to do the elliptic multiplication. You need to generate a point, otherwise it doesn't work. From sorry, here we generate the hash, okay, from the secret, so that we have a fixed length over that, okay, and then the multiplication happens from the point on the curve of the spending public key with the hash of the share secret. Now, there's this share secret still like up in the air. The share secret here comes from the ephemeral private key multiplied by the spending public key. You might say, hey, but where is the viewing key and all these steps? The viewing key is used to generate the ephemeral private key in our case. So the ephemeral private key is somehow derived from the viewing key.
How the third party can recompute the same sequence?
Only if, in this case, only if you have the viewing private key. And so if I want you to compute the address for me, I share with you my viewing private key, a node of it, okay? You then generate the ephemeral private key, and then the spending public key is public, so I can even publish on chain, it's not a problem. And then from here, you arrive to generate the stealth address. Again, there are even other methods to do that, but the idea is that only the spending public key is here, and this hash secret needs to be generated in a way that depends on the use case. In our use case, for example, you want a way that is pseudo-random generated for the use case, and this is why I use the viewing private key to generate this ephemeral private key. And do you remember that we use the nonce 0, 1, 2, 3, 4 for the different addresses? A different nonce will generate a different ephemeral private key, and this is why the secret changes, and this is why the final address changes. It's like a butterfly effect from the nonce. When it comes instead to the other way around, it's quite easier because we have already the ephemeral key generated. Okay, so like you generate the private key, you also have a public key of this ephemeral, and then when we go to generate stealth private key, that's the function. You already have the ephemeral public key, you have the spending private key, and that's you compute the same. If you take this share secret and the other one done the other way, they're exactly the same. And this is something that you cannot change. This is a mathematical constraint. This is how elliptical multiplication like basically works with a share secret. Then you hash it. And then the operation is slightly different because we are working with private keys here, not public keys. But under the hood, you can think is the same. Is elliptical multiplication with a module that limits its size on the curve. Otherwise, you can have values that goes out of the max available for a private key.
Okay, but you need to store somewhere ephemeral public key, right? In storage.
Yes. So in our case, since it's pseudo-random generated, we can always recreate. And this is also why we were returning from the generate stealth address. This is why here we were returning, sorry, my bad.
Okay, I think I got it. So this ephemeral public key array you generate using HD path for the
pretty much exactly.
Yeah. Okay.
But then with ERC5564, for example, the public key you could put that on chain, and then only if you have the private spending key you can then also like regenerate this address and see that it's your address basically. So yeah, there's definitely different ways to go about that part as well. Yeah.
And this is the part I was speaking before about based on your use case, you can adapt one or choose another, or you even find a third path that we haven't explored yet and do that.
Okay, okay, thank you, got it.
You're welcome.
Right. Awesome.
Yes.
Thank you, everyone.
If you need more questions, you're